Okay, so it's a great pleasure to be here at this Jonathan Dowling Symposium. And so I think I have the distinction of knowing John the longest because he and I became friends in 1989. I'll say more about that in a moment. So I'll say more, but I've known John, that would be 33 years ago we met, and he was a young man. And unlike a lot of the stories you heard, he and I are close to the same age. So yeah, so I knew him as more of an equal than well, never an equal, but contemporary. Okay, so what I'll talk about now, this talk is, I haven't talked about this particular, the first time I'm giving this talk, so it'll be a little bit imperfect, I would say. But it's really related to work I did with John. So it's very motivated by that. I'll talk about the role John had in this and what we did with it and why and how it relates to his books and everything. And it's a physicsy side as opposed to the quantum information side that tends to be more prominent in more recent discussions. Okay, see if I understand this. Okay, so this one I thought I would just, this is not related to the talk, but I thought I would just tell you something about John that could interest you. So when I met John in 1989, he'd finished his PhD a year before, and he was he became a postdoc. But I knew Asim Baroud, who was his supervisor, and I knew John's PhD work. And so I just thought I'd put this up to tell you what happened. So I met John in 1989, and this somehow, I know Dan's giving me a breakdown of the pointer, but I think I'll just use my hands. Oh yeah, okay. I'm going to use my finger. I'm better with that. So this was the conference. It was a NATO conference in Istanbul back in 1989. I was invited there by Marlon Scully. But the organizer of that conference in Istanbul was Asim Baroud, who was a supervisor, who was originally from Turkey. So then it was this NATO conference. John talked about stuff, but not related to his PhD work, but I talked to him about it there. And then what happened was very funny. Years later, John has a sister in Saskatchewan, which is next to Alberta, where I live. And it was easy to get John to come out to Canada, because if he came to Calgary, he'd visit his sister in Saskatchewan. And I had him out. And I brought him out. I said, John, can you give a talk? He said, sure. He came out. And then when he got in, I said, I want you to talk about your PhD thesis. And so John was really frustrated, kind of pleased about that. But of course, that was like 15 years ago. By that time, he forgot his whole PhD. And so instead of having a good time and enjoying himself, kind of things like Mark says, he disappears to Hawaii when he wants to have something to do. He had to sit there for days in Calgary remembering his PhD thesis. And I studied his PhD thesis again so I could ask him hard questions in his talk. So that's what happened. And then just to tell you, since his PhD thesis, even John forgot it, but I really like it. I'll just tell you briefly what he did, and then I'll go into the other stuff. So you can see here, this is one of the papers that came out of his PhD. This came out in 1986. It's one of the earlier ones. And it's quantum electrodynamics based on self-energy, spontaneous emission in cavities. And so Baroud was a follower of the thinking of people like E.T. Jaynes. Jaynes Cummings we hear about, but we think of Jaynes Cummings in quantum optics and all that stuff, but Jaynes was actually the last rational holdout, I would say, on quantum field theory. So Jaynes was part of this school of thought where he says, okay, I believe in quantum mechanics in the sense of first quantization, but not in the sense of second quantization. So he rejected quantum field theory, but he was playing a game. He never really rejected quantum field theory, but he said the proof wasn't there. And if you go back and read the Jaynes Cummings paper, the original from 1963, you can see the words there from Jaynes, where he's saying that the amazing thing is that even when I quantize the atom field interaction, I don't need to quantize it. So he kind of raised the challenge, which wasn't satisfied until the 80s or 90s, depending on what side of the fence you're on, demonstrating that the Jaynes Cummings model really demonstrated entanglement between field and cavity. So Jaynes was like that, and Baroud was in that school of thought. And what they would do is say, instead of quantizing the field, they would take like electron motion or atom, and then they would deal with the radiation reaction. Like an electron, if you treat it like an almost point particle and it acts back on itself, you can almost reproduce the quantum effects. It's different in terms of prediction, but it's testable. And so the thing that Baroud and others wanted is whether, they wanted to see a real proof that this self-action, self-interaction would not affect things. And so that's where John really got started. And so over here, it says QED, quantum electrodynamics, but the quantum in this case is really the quantum of energy levels of the atom. And then this is how it worked. they would be the Einstein A coefficients over here, and they would depend on form factors that depended on the wave function. The wave function you'd write in terms of how the electron behaved in the atom or outside. And then what they do here is he says, what if the atom is in a spherical cavity? He calculates the T values and then determines the Einstein A coefficient. And the Einstein A coefficient, if you're a quantum information person, then there's, well, how about T1, T2, or spin flips or phase flips. And so essentially, this is just a calculation to check whether the Einstein A coefficient just tells you you're getting a flip and how fast it happens. So do you get an exponential curve, and what is the coefficient? And these theories don't quite get exactly that, but that's the idea. So that's where John was. And so I knew John's work way back. And so I knew that he was an excellent, hardcore, theoretical quantum optics type person. So when I'd meet him in the early days, we would often talk about these kinds of things. And he was always, he always talked about how much he enjoyed doing this foundational work. But when I would pin him down and discuss, sometimes he wanted to forget about that stuff, but I like it. So that was it. Okay, so what happened was years later, this is the paper I'll talk about. So this is my one paper with John Dowling. Phys Rev Letters 12 years ago now. And it was with Pyotr Anisimov, who was a postdoc at LSU, and with John. And what happened, and I'll tell you more about it in a moment, is there was an experiment done with superconducting circuits that claimed to see electromagnetically induced transparency. And I feel badly, it was Nakamura, who's famous as being the first one to see that the superconducting circuit can behave like a qubit. And so, and I was in Japan, and Nakamura was saying to me, here's our result. Do you think we saw EIT? And I said, yes, I think you did. And then paper came out, and I'll say more about that in a moment. And then I just kept beating myself up because I thought, no, they didn't see it, but they did see it. And I realized I didn't really understand EIT, that's electromagnetically induced transparency. And so then what happened is I went on one of these famous boat trips. Who was talking about it in the break? Hafnian and all that. So John had lots of stories about his trips on the Volga River. Olga Kocharovskaya used to organize them, and I used to call him Olga on the Volga trips, and I went on a couple. And so you go on these trips, it's go through northern Russia in the middle of summer, so the sun never goes down, nobody can sleep, and everybody's in the bar on the boat drinking vodka all night long because the sun doesn't come down. And it was the perfect trip for me because it had all the world experts on electromagnetically induced transparency, and nobody could sleep and nobody could get off the boat and escape me. So what I would do is I would just go haranguing everybody. And I remember talking to Zuhal Zuberi and lots of other people. And unfortunately, like a lot of the great work in EIT actually came out of Russia. It was Nizhny Novgorod. So it was a good chance to talk to people. And the one I harangued the most was Pyotr Anisimov, who was a postdoc with John Dowling at the time. And I used to sit down with both of them, and we would talk every day, every night about this, and I just wouldn't let it go. And so the idea, and I'll explain more, is, and I'll explain what electromagnetically induced transparency is, but the question was, are they seeing this or are they seeing that? And what makes the difference between this and that? And none of the quantum optics textbooks, I feel, ever made it clear. And the textbook writers were on the boat, like Scully, Zuberi, and others. And so I had them there, and then I pinned these guys down, and Pyotr came out of Nizhny Novgorod, so he really understood the physics. And so over here in the abstract, you can see it says Otler-Town splitting and electromagnetically induced transparency both yields transparency in an absorption profile, but only EIT yields strong transparency for a weak pump field. But what does that mean? Strong. How strong is strong? Superman is strong. Schwarzenegger was strong, but Superman's a lot stronger than Schwarzenegger. So how do you decide what's strong? And weak. I won't go into weak people, but you got the strong ones. And so the question is, how do you decide it? Like you go to somebody, you say, well, if it's a weak field and you see a transparency, then it's EIT. Well, I don't know what that means. So eventually what we did is we realized it came from statistics. We're thinking, okay, you got to make a choice between two theories. How do you do that? And you do it based on Kullback-Leibler divergence. Maybe you don't know it, but if you're a quantum information type, you've heard of relative entropy. Relative entropy is the term for Kullback-Leibler divergence, which carries over to the quantum domain. And we did hear from people, including Peter Koch, about Fisher information. And I don't know if you know, but the Fisher information limit comes out of we talk about the metric. If you extend it, do you know this? The Finsler manifold and okay. So it turns out that the Fisher information is the limit of Kullback-Leibler divergence. So I'm still trying to understand that. But you talked about information geometry. And so the idea here is that somehow you have to make a decision. which theory is right, which is wrong. And I thought, okay, if people are doing experiments and claiming one and it could be the other, how would we do it? And then we spent our time on Aka-Ikei's information criterion. And that's just the callback library divergence. If one theory has 3 parameters and another theory has 4 parameters, who was it who said if you have enough parameters, you can fit an elephant? Do you remember that, Nana? What? Von Neumann, yeah, if you have 5 parameters, you can fit an elephant, and if 6, you can wiggle its trunk, something, yeah, okay. So Aka-Ikei's information criterion takes the problem of callback library divergence and says if you put more parameters in one model than the other, you pay a penalty. And so that's essentially what we did. And then we had our Otler-Town splitting, our EIT. We looked at experimental points. These are all related with the superconducting system. And the question is, with their noisy data, which one are they seeing? And with callback library divergence, you have to prefer one to the other. So if they say we see EIT and you think they don't, one is the null hypothesis, the other isn't. So this is the main effect of this work, is we said you have to be objective. You know, if you're going to claim one or the other, you have to know which model you're doing. Okay, and then this is the a paragraph, which I blew up. Is the font big enough for the people in the back? This is the visual version of John shouting. Okay, so coherent processes in atoms and molecules, many interesting practical phenomena. Anybody who knows me knows I wouldn't write that because the word many is imprecise. But it talks about coherent population trapping, lazy without inversion, electromagnetically induced transparency, and so on. It goes down, and then it says, nowadays, people are seeing this in quantum dots and nanoplasmonics, and superconducting circuits, metamaterials, optomechanics. So suddenly, in about 13, 14 years ago, all these experiments came out outside of the optical domain and started to see all kinds of effects that were in new systems, and the data were not good. So how do we deal with that? Okay, this is a textbook explanation of EIT. This is what you would learn if you go through a quantum optics textbook, and it's good conceptually, but it's not good enough to be able to discriminate. And so the idea here with electromagnetically induced transparency is you have a signal field and a pump field, a nonlinear medium, and then by tuning this, you can make it transparent, the signal gets through, or opaque, and the signal gets caught in here, and then release it later. And this is behind quantum memories and slow light and all that kind of stuff. And then mathematically, we have 2 ways of treating it. One is we'll take a 3-level system. We'll say that we have a probe field on resonant between a ground and excited state. Another, this is a control field between them. Probe could be weak. So seeing transparency for a weak probe is where, weak control is where we see this. And then what we can do is go to what's called dress states. We just diagonalize the Hamiltonian. And then instead, we still get a 3-level system, but we can talk about 2 excited states. And so in this picture, the transparency arises because you excite a superposition of 2 states. And if you do it in the right way, then and right way refers to a ratio of these Rabi frequencies for these fields, then you'll get interfering decay, and it won't decay. And I'll explain a bit more. It's actually in Fano interference. So Ugo Fano won a Nobel Prize for this. I always tell my students that, you know, if you want to get through a PhD with me, you have to know every Nobel Prize in physics. So when I tell you that, if you don't know, it's your fault. You wouldn't get the PhD in my group, unfortunately. Okay, this is the way to think about it, that this blue is the absorption line, red is the dispersion. Absorption and dispersion are related by Kramers-Kronig relation. Who knows Kramers-Kronig? Okay, no. So it's important. So do you know that you can't send information faster than the speed of light? But what guarantees that? And the answer that guarantees it is because Maxwell's equations are complex analytic. They obey Cauchy equations. And and the Kramers-Kronig relation just emerges. It says, if the Cauchy equations hold for Maxwell's equations, then your absorption and dispersion have to be related. This is why if you do spectroscopy, you might do absorption spectroscopy or dispersion, but you don't have to do both. Because if they don't agree, then you have a causality problem maybe. Okay, so this is if the blue line went up, you'd see a typical Lorentzian line shape. That's the absorption. But then if you tune it, you can create a transparency window in between. And then the dispersion curve here has a certain behavior. And what's nice is if you then take the derivative of the dispersion curve, you can get the group velocity. It's related to that. And these are straight lines. And what happens is by making these steep enough, you can not only trap the light, but by making this steep enough, you can stop light. That was 1988 or 1989. Lena Howe at Harvard University, her PhD was on that, and that was stop light. So there's a lot of physics that goes on in this. But the question for us is, if somebody sees a transparency window, does that mean it's this physics? This is the problem. And so the experiments coming out about 13, 14 years ago are saying, we see this kind of induced transparency window, therefore it's EIT. And so we need to go a little bit beyond the textbook case to understand. This was the experiment that came out. That was 2010. And you can see here, Nakamura and Tsai was the experimental group, Yuri Pashkin, Zagoskin. By the way, Zagoskin was the professor, he was at UBC, University of British Columbia. So he's the person behind the original D-Wave founding. Astifia and Abdu Malikov was the one who gave me the data. And this is what I feel really badly about. They talked to me about it. I talked to them about saying, yeah, I think it's EIT. And then I said later, just, can you give me your raw data? Like, you can see the kinds of curves. And the question is whether we're seeing electromagnetically induced transparency. And they gave me the data. And I said, look, it could be that, you know, what you got, I might not agree with it. I might write a paper saying you did a bad job. Are you okay with that? And they said yes, because they were probably sure I was going to do a good job. I find out they did a good job. Anyway, they did a bad job. They did a good experiment, and it was induced transparency, but it wasn't what the title said. And I lose sleep over this. I feel badly about doing this, but that's what happened. So they say we present experimental observation of EIT on a single macroscopic artificial atom. So their 3-level system looks like this, and they managed to get induced transparency, and it's done with microwave fields in a superconducting system. And it was actually, at the time, a really good experiment, very technically challenging. Seeing it was hard, and so it was really excellent work. It's the question, people were just confused about what EIT is. And so this was the point that I raised with John and with Piotr at the time. We went through it, and we were trying to figure out, okay, with the raw data, is it really EIT? And then, sometimes I'll put some pictures up. I've got I'm preparing, I get bored preparing a talk, so I look up pictures. I look up things, like fiddling around to try to do stuff. So this is Tobias Kippenberg and his group. And you can see this paper was out in Science in 2010, optomechanically induced transparency. So people started renaming it, but whether they're seeing EIT or ATS matters. But look at the curve they get. You see that? It's like infinitesimally thin. So the transparency window is extremely narrow. So there was no doubt in my mind they're seeing what they want to see. I never bothered looking at their data. It was, it was perfect. There's not other towns, and I'll explain why. Okay, so that was it. And also, now this is the interesting thing. So then if you start to think, what is EIT and when was it done? You can go back to Willis Lamb. Willis Lamb won a Nobel Prize. Do you know this? So you should know his work. So Willis Lamb and Rutherford started to develop an EIT-related method to study the fine structure of hydrogen. They, because they care about the Lamb shift. So the idea is to try to measure it better and look at this curve that they get when they essentially, I won't go into the physical details, but they start to do this 3-level system type thing with hyperfine splitting. And they're seeing what by our calculations, if you believe my definition of EIT, then I would say 1950 was the first year to see EIT. And what's interesting is they explain the effect in their paper by saying we can understand it electrically and classically. There's nothing quantum about it. This is an inductor. This is a capacitor, inductor, capacitor. There's a resistor on the left, but not on the right. And so the idea here is they're saying what's going on is that these dips are occurring because 2 harmonic oscillators share the same reservoir. That was the key point. So they're dissipating into the same reservoir. That's the same thing with address states. They're both decaying in the same reservoir. They interfere. So then it's very interesting. This paper came out in 2001. This is Paulo Nussensweig in Sao Paulo, Brazil. And he and his team did a very nice paper. It's American Journal of Physics. They didn't know or refer to the Lamb and Rutherford paper, but they said, how can we teach EIT to university students? And we do it by, and here they have a similar picture, coupled oscillators, but they said, they didn't say this is EIT. They say, this is a classical analog to EIT. And then this is the mechanical oscillator. But the mechanical oscillator I'll show you, in fact, I think I showed you, that was, yeah, that's in here. This model from Kippenberg's group on optomechanically induced transparency is essentially this model over here. And so they went through it. So then the question even comes up, do we really even need quantum mechanics to understand EIT? I'm in the camp where I think it's classical, but I have a lot of heated arguments with people, like people who, especially quantum optics, people who wrote quantum optics books say no. And either I'm really obtuse or they're wrong, but I'm never convinced. Okay. So then here's the Otler-Townes opposite side. Townes, by the way, won a Nobel Prize for the maser, so you know all his work. And it's interesting. They did what's called the Otler-Townes effect, and I learned it as the AC Stark effect. But what happened is they invented that, and they said they took the Stark effect, and then they called it the AC Stark effect. But it's nothing to do with Stark; it's their effect. So we mistakenly talk about AC Stark because Otler-Townes did that. But I don't know if you know, Stark was a Nazi too. So I'm not fond of that, his politics. So I never talk about AC Stark anymore. And so Otler and Townes wrote this paper, which they called a Stark effect. And this is the other effect that's coming up. But the idea that it's related to EIT is not inherent in their paper. So we have Otler-Townes and we have EIT. This is the first experiment to see EIT, unless you believe what I said, that the Lamb and Rutherford paper saw it. But this paper is amazing in that they had to be able to get a common reservoir for decay of the two uppercase levels. That's Atash Imamoglu and that's Steve Harris. Over here, this is the three-level atom, but this one is from Piotr, John, and me, where we're building the three-level atom, but we're putting in the probe field Rabi frequency, the control field Rabi frequency, detunings, decays, and so on. So we're saying, if we write this three-level atom correctly, can we connect these two together? Now, we're not the first to do it, but this is the way we're starting to analyze it. And then if you vary the parameters, you can get an effect here with a narrow dip that would be EIT, or a wide dip that would be Otler-Townes splitting. And so the question is this just two extremes of parameters, or is there different physics going on? And I'll point out why it's different physics. So, and the essence of it goes back to Ugo Fano. So this is Fano's Nobel Prize winning stuff, where it's essentially Fano realizing that if you have the physics of two energy levels decaying into the same reservoir, it's different than they decay into different reservoirs. So this is what distinguishes the two. And here, what happens, you can solve these quantum master equations and trajectories and all this stuff, but you don't need to. You just write the quantum master equation, do a Laplace transform, and then study the Laplace transform of it. And what you find with Otler-Townes splitting is you get a Lorentzian plus a Lorentzian. And what you get with EIT is the Lorentzian minus a Lorentzian. So the different physics, when you look at an experiment, is this is the model checking where this Kullback-Leibler divergence idea comes in. But what you'll see here, delta is a variable. You get three parameters and four parameters. So we have to penalize the different number of free parameters to fit. And then the question is, when you do an experiment, are you seeing this or are you seeing this? This is ultimately how you have to make the decision. Okay, now the physics of it goes back slightly earlier. This is Piotr. This is from his PhD thesis with Olga Kocharovskaya, who organizes the boat trips. And then they had a paper in a Journal of Modern Optics. It was, I forget who it was for, but it was a special issue. And they say it, but their paper is not very clear. Like when you read it, it's hard to extract from the paper the physics, but it's all there. And meanwhile, 2010, there was also a paper I really liked, EIT and Otler-Townes splitting, two similar but different phenomena. And then a couple of days ago, I thought, what happened to Tony? So I never met him. I love his paper, and I wrote to him. And he was enjoying physics so much, he decided to become a realtor. So he uses his quantum physics now to sell real estate in Pennsylvania. And then he and I have been corresponding, and I sent him the talk, and he's very excited. So he's very excited that right now I'm telling all of you about him because he thought physics was behind. And he told his wife, and she's excited. And he was almost tempted to get on a flight here just to see this. So that was it. But he seems like a very good guy. I never met him. So he wrote about it and got some of the physics right there too. Okay, now the work that John, Piotr, and I did, and the questions that came up started a flurry. So we got some good citations. I don't care about that, but John cares about that because that was one of the things we talked about. He liked getting cited. And then what happened, this is just a sample of papers. You can see Nature Communications, Franco Nori, Lanyang, it's what is and what is not electromagnetically induced transparency. So they're asking the question, do we have EIT? You can see this paper that came out of University of Post and Telecommunication, discerning the two. Another one here, which one is it? And so on. And a lot of papers came out. And suddenly it became a big field where everybody said, which one do I have? And they found ways to revive experiments on EIT and then asked which one they had and tune between them. This is Georg Reitel's group in Ann Arbor, Michigan, transitioned from EIT to Otler-Town splitting. I should have put one up from French group, Elizabeth Jacobino, there was another, various others, but a lot of people went back and did their experiments, very motivated. They wouldn't have done it, but John went to every group in the world and said, you should do this. So he went around as a proselytizer and made sure anytime anybody said EIT, I said, you have to do this experiment. So they did it. So I became famous out of it just in his coattails where he proselytized. And then this, I don't think I need to read, but this is interesting. It goes through, and this is Georg Reitel's group, and they do this EIT test. And they write about it in the abstract of what they did. But this relates to something that ties in with what John did. So up above, self-promotion, this handsome guy with a suit on is me, in case you don't recognize him. And there's Alex Zabowski, Wolfgang Tettel back when we were setting up in Calgary. I figured we need some teamwork. So the three of us managed to get along briefly and write a paper that was in Nature Photonics and Optical Quantum Memory. And so we're kind of setting it up. And you can see here, it says optical delay lines, cavities, electromagnetically induced transparency, no Otler-Town splitting, right? So the concept when we wrote our paper back in 2009 is you use EIT. This is out of John's book, Schrodinger's Killer App. And he says, self-induced transparency, that was what Steve Harris's group called it when did it. Now university called electromagnetically induced transparency, has been proposed as a photonic quantum computing medium. And then John goes down, he says, there are, however, proposals to exploit storage capability of EIT system for quantum memory, but note there's no Otler-Town splitting mentioned because the concept wasn't yet clear. And here's John again, you recognize the guy. And then this is his other book, and he says, a poor person's quantum memory is made by taking the input photon and put it in a fiber loop. It goes round and round, but it doesn't help because it'll lose it. And then he has says, put a type of quantum error correction in the loop. So he's saying, I'll do quantum memory by putting a photon in a loop. It goes round and round, and I'll keep interrupting with quantum error correction. Not very reasonable, but it's because the EIT seemed too hard. Then, again, based on our work, this is by Lindsay LeBlanc's group in University of Alberta, which is 300 kilometers from Calgary, which to us is just hop, skip, and jump. It's like next door. And so they did the work here where they had this Nature Photonics paper where they did it all by Otler-Town splitting. So they said, we don't need EIT. If Otler-Town splitting, if we get rid of EIT and we do Otler-Town splitting, we don't have to make sure that the radiation is in the same reservoir. It's okay if it radiates into two reservoirs. And so that's what they did. And they show here, so is it good enough? They're saying, well, why don't we use ATS, Otler-Town splitting instead? And it's good enough. They go through and they conclude that it works, and they say that's going to help in a lot of areas. So then the interesting question that comes up is, do you even need EIT once you distinguish between the two? And then they explain it more here. In this paper, they take this kind of method we developed, and then they're saying, well, now let's turn it into, instead of, is it EIT or ATS, which kind of quantum memory is? So this paper, they go back and they say, now we even have a test for tuning this quantum memory. Now here, this takes us out of atoms into other fields. This is work I really like. Over here is Vladimir Manicharian at University of Maryland. This is Michel Devoret at Yale University. And so back when Vladimir was Michel's student, they invented something called fluxonium. Fluxonium allows you in a superconducting system to make a multi-level atom. So if you like multi-level atoms and you want to do it in a superconducting system, this is the way to go. There's a lot of technical problems, but for me as a theorist, it's very enticing. And so we started thinking, okay, well, maybe let's think about EIT in superconducting systems. And it's got some interesting features for a theorist. Instead of three-dimensional modes, it's one-dimensional. So the physics, you no longer have absorption, right? So in one dimension, what you'd call absorption and dispersion just becomes transmission and reflection. And so we started looking at the system. And because in the one-dimensional system with artificial atoms, the selection rules change. So like with a 3-level atom, you can easily start to couple different pairs together and play with it. And so in this work, and by the way, Alexander Blay is on this. He was a undergraduate project with, what did I forget the name? The one who started D-Wave. Okay, I forgot already. I showed you in the slide earlier. Okay, anyway, so we do it. And then what we found is that if we can play with that level, we just generalize the master equation to include another level of control. Thanks. So we generalized to include another level of control, same Laplace transform analysis, we start to get amplification, which is interesting because then you can start thinking about quantum memory, and quantum memories are lossy, but you can start to amplify. Anybody who knows the physics of these things will immediately worry because first of all, amplifiers are noisy, and second, they do frequency pulling. So when you store, there's a pulling effect at different frequencies. And the idea here was to use fluxoniums to be able to do it. But then fluxonium wasn't doing well. The experiments weren't working perfectly. So later, Patrick Loon was my postdoc, and we decided to do a string of other kind. Basically, we analyzed 5 artificial atoms on a microwave line to study this and proposed the ways to store, control, et cetera. Again, all of it coming out of work, thought of with John. And then I had a student, Hessa Al-Taibi, came from Kuwait. And she and I, her whole PhD was on double-double electromagnetically induced transparency. So what we thought is if one window is good, 2 windows are better. Because then you can start doing bichromatic photons. Why not make your qubit a superposition of red and blue light, that kind of thing. So we did it. And then, so we have the double transparency, and we have 2 windows and 2 frequencies. And so we did a set of papers on that. Since it's getting to the end of my talk and we're supposed to joke a lot at this meeting, I thought I would just tell you why I called it double-double. So I don't know if you know, but to Canadians, the most popular coffee chain is Tim Hortons, and they serve a double-double. So lucky for me, these all landed in American journals. And I don't think they know Tim Hortons that well, so we got away with nobody knowing. John would have been proud. Okay, then later I thought, well, the superconducting systems weren't working well. And I have a part position in India at the Raman Research Institute. One of my collaborators there is Andal Narayanan. She and I are going to I hope everybody's writing special papers for the special issue. Sishin, right? Everybody's agreed to do it. Okay. Her eyes were closed. Okay, anyway, so Andal and I are working together on it. And I went to Andal in India. Andal was doing really good work where she puts atoms in microwave cavities. And so with the system she developed, we could see that she could drive the 2 lower levels with microwave transition with excellent phase control and all the rest. So we started working together on that. Lambda system is the 3-level. We call this delta, where we combine all 3. And so with the atomic delta system, we're able to get, this was switching, and then phase sensitive amplification of an optical field, and microwave-driven generation and group delay. So in Andal's system in Bangalore, India, we're able to do very nice work where we're actually realizing some of the controls that first came to my mind back when John and I were collaborating. And then there's a nonlinear side, how to slow light and do nonlinear interactions, playing with levels. These kinds of questions come up. This goes back earlier, 2006, where you can see you can use much more complicated levels. If you do it, you can start doing quantum memory combined with nonlinearity. And I won't go into it, but being able to do nonlinear interactions. Who was saying talk? I mean, we had a few talks, but the idea of linear optical quantum computing is to avoid nonlinearities. But nonlinearities are still a possibility, so it's worth investigating. Or are they? In fact, the first question that came up about this is work that nobody seems to know about, which when I was a postdoc with Jared Milburn at the University of Queensland, I was just admitting shamefully to some Brisbaneans just during the break that, yes, I lived and loved Brisbane. And so this is the Brisbane days of my life. And so we were looking at these limits. Later, there was some very beautiful work. Jeff Shapiro, Julio Febanacloche questioned whether it's physically possible to do nonlinear quantum optics at the level needed for quantum computing. The trick you always do is, if you make everything narrowband, you could do nonlinearity, put it in a cavity. Trouble is that every gate takes infinite time. So that's the trade-off. Okay, but notwithstanding those problems, people look at that. So this is work David DiVincenzo and a student back in 2010, where they're converting this over to superconducting systems. So one nice thing is if you understand how to turn three-dimensional spatial reservoirs to one dimension, a lot of stuff can be mapped over to this domain. And then this is my final slide. I'd like to leave time for questions, arguments, debates, fight. And so the summary, first of all, these are the four. So if you, whatever you do, this is the takeaway message. So first of all, electromagnetically induced transparency and Otler-Town splitting are related but distinct induced transparency. So they're different physically. They're different by whether Fano interference occurs or not. They're extendable to double-double, to delta systems, et cetera. They have applications to nonlinear optical switching, optical quantum memory, which my colleague at the University of Alberta in her Nature Photonics paper, that optical quantum memory. And to give credit, Erhan Saglam-Murek, who's now at Berkeley, was her postdoc, and a lot of the ideas came from him. Bichromatic qubits, so can we start storing superpositions of two colors and so on. And these delta atoms that I talked about, so the lambda atom with microwave driving here, or in superconducting systems, you get it for free by not having selection rules, have very rich physics, such as phase-sensitive amplification. So there's actually a lot of physics there. And the journey came with me, Piotr, and John on the boat all night long, sleepless, vodka enriched, and really starting to question a lot of the paradigms in quantum optics. Nothing we did is really hard from a theoretical level. It was a matter of just erasing the concepts from our brains and going back and thinking creatively about it. So I managed to do many years, I've managed to squeeze a lot of value out of my conversation with John. Thanks.
Any questions for Barry?
Thank you very much. That was very entertaining. I have a question about the nonlinear optical switching. Is there a way to get like a trade-off, like at a high level, like a trade from high level, but certain speeds and the loss of an optical switching? Is that something that can come out of EIT versus Otler-Town?
Yeah, excellent question. This is something I think a lot about, and I never get anywhere. Yeah, okay, do you think about this? We can commiserate sometime. Yeah, so first of all, it's interesting when you raise the issue of Kramers-Kronig for the nonlinear optics, because the first problem is not that straightforward. In fact, I don't know if you know that Peter Drummond and Mark Hillary wrote a book on nonlinear quantum optics. Yeah, if you know this. Yeah. So the problem is, oh, and who was talking? Was it Nick? You here? No. Yeah. That was weren't you saying about the canonical momentum, right? Yeah, that's the same problem, right? So when you're saying the canonical momentum, I was thinking partly about this. So if you pick up a textbook on electromagnetic theory, what are the conjugate variables? Vector potential A, electric field E, but it's not right. And this is why Maxwell's best result in electromagnetism was introducing D. So, you have this conjugacy between it. What is D? D is the electric field with the polarization in the medium. So then what do you do with the nonlinear system, right? The nonlinear system, you have a nonlinear expansion, like a Bloombergian expansion, which is not fundamentally correct. It's just a perturbative treatment of it. And so even when you come, and then you say, what about a Kramers-Kronig relation that comes out of preserving causality for the electromagnetic field and Cauchy equations? And even the question, and this is what Mark Hillary and Peter Drummond write about, and Peter did a lot of, Peter Drummond, right? He was at University of Queensland for years, and he's now at Swinburne University in Melbourne. So, but he's a New Zealander. Don't just because he lives here doesn't make him Aussie. And people, I'm an Aussie. I'm both Aussie and Canadian, so I can put down New Zealanders. Yeah, so he's at Swinburne, and they analyzed it. And this goes back. There was work in the 70s. It was Hillary and Mladenov. Yeah, Mladenov became famous later because he wrote Star Trek movies and things like that. Who's that? Oh yeah. Yeah. So Leonard Mladenov lives what's Alhambra, right? Or Pasadena or somewhere in Pasadena. Yeah. I met up with him there. Yeah. So he went from writing about conjugate E and D to writing science fiction, which was only a small jump. And so, yeah, Hillary and Mladenov were the first to address that issue of the conjugates. Yeah, I remember your postdoc work. Did you touch on that? You were doing the two-dimensional. Yeah, it might be from you that I first heard it. Okay. Yeah, so that's the problem. Then you go and you say, what about the physics of nonlinearity? So it's really a deep question. You know, what are the limits with nonlinearity? And even getting these canonically conjugate variables is not that straightforward. So that's my long answer with zero content. That's why you said my talk was entertaining. You were saying, I learned nothing useful, but you made me laugh. So I just, yeah.
Maybe one more question if it's a short answer.
Well, like, how about no answer? We'll just go to questions and no answers. Yeah. Yeah. That's, yeah. So the question was, is there a way to see ATS, not just the IT? That's what those papers, I said, somewhere along the way, ATS, blah, blah, blah. I did too much, didn't I? Somewhere along the way, I give up. Somewhere along the way, I said there was a whole set of papers. So yeah, you can basically, if you make EIT or in optomechanical systems, you get two energy levels that radiate, lose energy in the same reservoir. You just have to add noise to it. Then you destroy the coherence, you remove the Fano interference, and you recover ATS. So that was what a whole slew of papers did for years, is saying we worked really hard to make EIT, now we're gonna mess it up. Thanks.